Hey everyone, in this video we're going to learn how to factor the difference of two squares. As a warm-up, we'll start by simplifying each of the following expressions. First we have x minus 6 times x plus 6. We'll start by distributing the x. So we have x squared plus 6x, and then we'll distribute the negative 6. So minus 6x minus 36. Now we're going to combine our like terms, so we should notice that plus 6x and minus 6x are going to simplify, and they'll cancel each other out, and we're left with x squared minus 36. Next, we have 10 minus x times 10 plus x, so we'll distribute the 10 to start. So we have 100 plus 10x, and then we'll distribute the negative x, so minus 10x minus x squared. Combining our like terms, notice that positive 10x and minus 10x simplify and cancel each other out. So we have 100 minus x squared. Last, we have x minus 2y times x plus 2y. We'll start by distributing the x. So we have x squared plus 2xy. This is a good opportunity to remind you when we're multiplying variable terms together, we typically like to write them in alphabetical order. It's going to be helpful in identifying like terms later in the problem. Then we'll distribute the negative 2y. So we have minus 2xy minus 4y squared. Combining our like terms in the middle, the positive 2xy minus 2xy cancel, and we're left with just x squared minus 4y squared. So notice each of the products. We have x squared minus 36, 100 minus x squared, x squared minus 4y squared. See if you notice any similarities in each of the products. And then look back at the original multiplication. X minus 6 times x plus 6. 10 minus x times 10 plus x. X minus 2y times x plus 2y. So hopefully you've noticed a few key characteristics that we're going to use to answer the following questions. The first being, how did the expression in the first set of parentheses compare to the expression in the second set of parentheses? So each expression had the same terms, but the sign or the signs in between the terms were opposites. Right, so we had x minus 6 and x plus 6. The same terms, x and 6, but in one expression it was x plus 6, and the other expression was x minus 6. The signs were opposites. What happened to the middle terms? So in each of them, they canceled out. Right, they simplified to be 0. And working in old properties, the middle terms were always additive inverses, right? Plus 6x minus 6x, plus 10x minus 10x. They were always additive inverses to work in that idea from earlier in the year. What sign is in the middle of all of the products? Subtraction. Right, think of our products. X squared minus 36, 100 minus x squared. X squared minus 4y squared. The subtraction between the two terms in all of our products. And what did you notice about the terms in all of the products? Well, let's think. X squared 36, 100 x squared 4y squared. So what I notice is that each of those terms is a perfect square. Okay, so noticing the answers to all of these questions is what's going to set us up to factor the difference of two squares. So defining the difference of two squares, otherwise known as dots, or often referred to as dots, and that just comes from the first letter in each of the words. If we have the difference of two squares, so we have a squared minus b squared. So hopefully we can all agree that a squared and b squared are perfect squares. The difference means subtraction between the two terms. We can factor them as a minus b times a plus b. We call these factors in relation to one another conjugates. Okay, so if two factors have the same terms, but all that is different is the sign in between the two terms. They're referred to as conjugates. And now, a couple things. Have to have the difference of two squares. So if we have a squared plus b squared, no good, right? That would be the sum of two squares. If we had a cubed minus b squared, no good. A cubed is not a perfect square. A squared minus b squared, difference of two squares. Okay, it could be a to the fourth minus b to the fourth, whatever it might be, as long as our two terms are perfect squares and we're taking the difference of those two terms, they can be factored, or that expression can be factored. Okay, and this also helps solidify that understanding that factoring is just the reverse operation of distribution, right? In that first slide, all we were doing is distributing, multiplying out. And now we're working in the reverse direction for each of those examples. So let's practice. Factor each of the following polynomials. So x squared minus 25. So first, do we have the difference of two squares? X squared and 25 are perfect squares. Subtraction, so we do. So we can factor this as x minus 5 times x plus 5. Right? Essentially, we're going to take the square root of each term and create conjugate factors. And we can check that this is correct. We can multiply it out. And again, I'll leave that as an exercise for you to work through to see that you get x squared minus 25. 16a squared minus 1. 16a squared is a perfect square. 1's a perfect square. Difference. Perfect. So we can factor. So the square root of 16a squared would be 4a. So we'll say 4a minus the square root of 1, which is 1. And then our other factor would be 4a plus 1, right? Conjugates. 9x squared minus 100. 9x squared is a perfect square. 100 is a perfect square. We have the difference. So first factor, square root of 9x squared is 3x. Square root of 100 is 10, so 3x minus 10 is the first factor. The other factor is its conjugate then, so 3x plus 10. 4 minus x squared. So now notice the variables in the second term, but that shouldn't change our approach at all. So first factor, the square root of 4 is 2, minus the square root of x squared, which is x. And then the other factor is the conjugate, so 2 plus x. Now, we could switch the order around, right? So say you write 4a plus 1 first. That's fine. Then your conjugate factor would be 4a minus 1. And the reason we can switch the order, going back to the beginning of this course, is the commutative property of multiplication, right? The order that we multiply two terms in doesn't affect the product. Okay, so just to write that out, let's say you had done 4a plus 1 as your first factor. Its conjugate would be 4a minus 1. Perfect. Still correct. Still equivalent to 16a squared minus 1. Next, we have 1 minus 121y squared. So 1 and 121y squared are perfect squares, and we have the difference of those two terms. So our first factor is going to be 1 minus the square root of 121y squared is 11y, and the conjugate of that factor is 1 plus 11y. Next up, we have x squared minus y squared. So we have a variable in each term. Doesn't matter. We still have two perfect squares, and we're taking the difference. So our first factor, the square root of x squared is x. Square root of y squared is y, so x minus y. And then our other factor is the conjugate, x plus y. Let's fix that y. There we go. Looks better now. B squared plus 9. Well, our two terms are perfect squares, but we no longer have the difference. Now we have the sum. So, this is not factorable. This is oftentimes referred to as a prime polynomial. Think of what a prime number is. It's a number whose only factors are 1 and itself. So b squared plus 9 in this example can't be factored any further. So really its only factors are b squared plus 9 times 1. So hence the name prime. But for our purposes, writing not factorable is sufficient. 36a squared minus 169b squared. Okay, so we have two perfect square terms, and we're taking the difference. So the square root of the first term would be 6a. Square root of the second term is going to be 13b. So our first factor is 6a minus 13b. And then the conjugate, 6a plus 13b. There we have the factoring of 36a squared minus 169b squared. 49x cubed minus 25y squared. So what I notice about this first term, in particular the x portion, is I have x cubed. And x cubed is not a perfect square. So if I don't have perfect square terms, I cannot factor using the difference of two squares. So this is not factorable, at least with the difference of two squares. Now it's actually not factorable at all. We don't have all of our methods learned yet. Next up, 81m to the fourth minus 4n to the 10th. Okay, so now our exponents are changing. So m to the fourth is a perfect square, and so is 81, so the first term's good. 4 is a perfect square, n to the 10th is a perfect square, so we're good, and we're taking the difference. So the square root of the first term is going to be 9m squared, and then minus the square root of 4n to the 10th, which is 2n to the 5th. So then our other factor is the conjugate, 9m squared plus 2n to the 5th. And this is a really good one to multiply out and check that you get the original answer to practice multiplying and practice our rules of exponents. Right? If we have n to the 5th times n to the 5th, remember we add those exponents. 5 plus 5 is going to give us 10. Next we have x squared times y to the 6th minus 9. So now we have two variables in one term. Well, x squared is a perfect square, as is y to the 6th. So combined, this is still a perfect square. And then minus 9. 9 is a perfect square. Okay, so the square root of the first term is going to be xy cubed, and then minus the square root of 9, which is 3. And then we're going to multiply that by the conjugate, which is xy cubed plus 3. Next up, a to the 16th minus 225b to the 22nd power. Okay, looking at our two terms, we have two perfect squares, and we are taking the difference. So the square root of a to the 16th is a to the 8th, minus square root of 225 is 15, square root of b to the 22nd power is b to the 11th. And we're going to multiply by the conjugate factor, so a to the 8th plus 15b to the 11th. Next up, 144 minus the quantity 3xy squared. Well, 144 is a perfect square, and if we take the quantity 3xy and we square it, that's going to be a perfect square. I don't think we need to simplify this. I actually think it's easier to do the way that it's presented. So we can factor this with the difference of two squares. Right? We have a subtraction here. So the square root of 144 is 12. Let's fix that weird looking 2. So we have 12 minus the square root of 3xy quantity squared is just 3xy. So that's minus 3xy. And then we're going to multiply by the conjugate, which is 12 plus 3xy. Next, we have a plus b quantity squared minus 64. So a plus b quantity squared is a perfect square. 64 is a perfect square. So we can factor it because it's the difference of those two terms using dots. So we're going to have the square root of a plus b quantity squared, which is a plus b, and then minus the square root of 64, which is 8. And then we'll have the conjugate, which is a plus b plus 8. Now in this case, we don't need the parentheses, the inner set of parentheses. So we could write this as a plus b minus 8 times a plus b plus 8. And it looks a little bit neater. Last two examples, x minus 2y quantity squared minus z to the 8th. Okay, so x minus 2y quantity squared is a perfect square, z to the 8th, perfect square, and we're taking the difference. So we can factor with the difference of two squares method. So the square root of our first term is x minus 2y, and then minus the square root of z to the 8th, which is z to the 4th. And then we're going to multiply that by the conjugate, which is x minus 2y still. First term stays the same. And then plus z to the 4th. And again, if we want to make our factors look a little bit neater, we don't need the parentheses in this case. So we'd have x minus 2y minus z to the 4th, and then x minus 2y plus z to the 4th. So a little bit more challenging, but if we keep our approach consistent, then we really should be able to handle any problem they give us, even these crazy looking ones. Our last example, 49 minus the quantity a minus b squared. Okay, 49, perfect square, good. A minus b squared, perfect square, good. Taking the difference of those two terms, perfect. So now we're going to factor with the difference of two squares method. So the square root of 49 is 7, minus the square root of a minus b, quantity squared, which is a minus b. Make sure you keep those parentheses around a minus b here. And then we're going to multiply by the conjugate, which is 7 plus a minus b. And if we want to lose the inner set of parentheses, well, in the first factor, we're going to have to distribute that -1. So our first factor would become 7 minus a plus b. And our second factor would be 7 plus a minus b. Now, we don't have to lose that inner set of parentheses, but definitely looks like a neater answer if we do. Okay, so that is how we factor the difference of two squares. With all of these examples, you should be able to distribute out your factoring to confirm that it is equivalent to the original polynomial expression, right? And that's always true with any factoring problem. It might take some time, but we should always be able to know if we are correct or not. So now it's up to you to practice with this method and do as much factoring with difference of two squares as you can. Click the Amazon link down below for my algebra workbook so you can practice on your own. Give the video a like, and before you go, click that subscribe button so you can see more videos just like this. Thanks for watching.